Can you hear me?
Yes.
Okay. We will waiting your friend in another maybe 2 or 3 minutes. Okay, in a few minutes. Okay, the class will start as 10 o'clock 35. Okay. Hello, can you hear me? Can we start now?
Yes, Ajahn.
Okay. From the previous lecture, I provide you about the detail of the Fourier transform. Okay. We start from the definition of the Fourier transform for a periodic signal. And later we extend the idea of the Fourier transform for periodic signal. Next one, we consider about the property of the Fourier transform and about the convolution property. Okay, the property of the Fourier transform will make you easy in the how to manipulate the complex signal. Okay, next one is about the convolution property, and another one property is the multiplication. Both property is very important in the engineering application. Therefore, I split two property from the overall property. In the previous I teach you the time shifting property, the frequency shifting property, the differentiation property, and so on. It maybe have about the 10 or 12 properties of the Fourier transform, but one of the most important property that make the Fourier transform and the other transform that very powerful mathematics tool in the engineering is the convolution and multiplication property that we will discuss in this section. The idea of the convolution property, you already know how to determine the direct convolution. If the signal input signal is a xt, the system have the impulse response s. you know that, okay, output will be equal to the convolution between the input and the system itself, okay, the impulse response of the system, okay. Now, if you take the Fourier transform of them, what happened to that, okay? And you know that, okay, when you determine the convolution in time domain, it's not easy, right? You fix one signal, flip another one, slide and integrate them, okay? Now, if we try to take the convolution in the frequency domain, okay, in this case, we apply the Fourier transform in the both sides of the convolution of equation, okay? The Fourier transform of the yt give you y omega, okay? The Fourier transform of this will be here, okay? The convolution, okay, yeah. Yeah, you take the Fourier transform of them, you integrate from minus infinity to infinity, multiply that signal by e power minus j omega t dt. The order of the integration can be interchanged, okay? Then the above equation can be simply expressed here, okay? We reorder from t and d and tau, okay? Sweep them, okay? And sweep the integration too, okay? Now we change, okay, the tau to be outside the bracket, okay? Now x tau that depend only on tau, therefore it's not depend on t, okay? You can see that x tau depend on tau, not t. Therefore, you see them as a constant, okay? If it's constant, when you integrate respect to t, it's not affects to tau, okay? You move them out, okay? Only ht that have both t and tau that affect by the integration, okay? Now, the x tau that depend only on tau, that does not depend on t, then the above equation can be simply expressed by here. Okay, after you reorganize them, okay, xc, yes, you can see that x tau is not affect on t, you can move them outside the bracket, okay, outside the integration. Next step, by the time shifting property, okay, in this case, when you integrate respect to t, right? Therefore, t in this case, okay, you can use the time shifting property, okay? If xt, the Fourier transform of ht equal to h over j omega, the Fourier transform of ht minus tau will be equal to e j minus omega tau h j omega. By the time shifting property, the bracket term is the complex exponential e power minus j omega t h j omega. And you can substitute this term in the above equation. Okay. Now it's here. Okay. Okay. H, you can integrate them, and this term will become the Fourier transform of ht or hj omega multiplied by complex exponential in the term of tau here by the time shifting. After you get here, you can see that hj omega is not affect on tau anymore, right? Hj omega, you can move them outside, okay? If you move them outside, okay, this term will be here, okay? And this term, when you see this term clearly, integrates minus infinity to infinity x tau e power j omega tau d tau is the Fourier transform of x, okay? In the Fourier transform of x, okay, it will become y equal to j, okay, it will become y equal to the Fourier transform of h multiplied by h. Now for the summary, you not need to prove that, okay? You can take advantage from the final answers, okay? The convolution of x and h that provide you yt, okay? When you compute in the frequency domain or the Fourier transform domain, it will be equal to exchange the convolution operation that very difficult to be a simple multiplication between the Fourier transform of h and the Fourier transform of x instead. That's why the convolution is very powerful to apply in the system analysis. Because when you have the input, when you have the system, we don't want to analyze them in time domain because the way to compute the convolution is very, very difficult. But when you compute them in the Fourier transform or the Laplace transform, you convert the input and you convert the system into the Fourier transform or the Laplace transform, and the output equal to a simple multiplication between them. Okay. Now, for the summary of the convolution operator is here. If we assume that, okay, xt have the Fourier transform of xj omega, and what ht have the Fourier transform of them h j omega. Okay, yt, that is the result of the convolution between x and h, will be equal to a simple multiplication between xj omega and hj omega. The convolution property is very important in the signal and the system analysis because the Fourier transform map the convolution of the two signals into the product of the Fourier transform. For the LTI system, or the linear and the time invariant system, the impulse response of the system HT can be completely describe the characteristic of the system. Therefore, the transfer function of the system Hj omega that you compute from the impulse response, or it is the Fourier transform of HT, can be completely describe the characteristic of the system too. Okay, that's why. Okay, if you know the impulse response of the system, if you know the input, you can find the output by its convolution in time domain or by a simple multiplication in the Fourier transform domain. Now, in order to make you understand, okay, we will provide you a simple example case. Okay, in this example, consider the LTI system that is characterized by the impulse response here. Ht equal to E minus AT UT, okay, and XT will be E minus BT UT. You can see that both signal is the decaying exponential. Therefore, it's almost impossible to determine them in time domain. When you determine them in the time domain, okay, both function is very difficult. You fix one of them, even though you flip another one, and you try to find the intersection of them, integrate them, it's not easy. Therefore, is have the alternatives easy way, okay, to compute them. Okay, the questions ask you to determine the transfer function of the system or Hj omega and determine the output or the response of the system Yt. The first one determine the system function, or okay, determine the system function of the system Hj omega. Evaluate the Fourier transform of the impulse response E minus AT UT. Okay, you can integrate them directly from the definition, or you can see them from the table. The Fourier transform of them equal to 1 divided by A plus j omega. Okay, and determines the output of the response. Yeah, the questions ask you to determine the output of the response. You know the system function. Okay, therefore you have two ways to do. One, you use xt and st. Okay, and you take the convolution in time directly, or you determine the Fourier transform of h and the Fourier transform of x, okay, and multiply them. Okay, in this case, we determine the Fourier transform of h and Fourier transform of x, okay, and evaluate the Fourier transform of the outputs y by a simple multiplication between Hj omega and Xj omega by here. After you get here, okay, you can use the partial fraction technique. Okay, you can see that make them to power 1. Okay, if the each factor is different, okay, you can use here. Okay, you can see it's okay by as the polynomial form. Okay, here you multiply both sides of the equation by a plus j omega and b plus j omega. Okay, in order to eliminate or destroy the denominator term. Okay. After you did destroy the denominator term, okay, in the right hand side, you can distribute a j omega, b j omega into the bracket of the k1 and the k2. Okay, and you can, okay, you can eliminate the denominator of the right hand side too. Okay, after that you distribute them. Okay, when you distribute them, you can see that, okay, left hand must equal to the right hand. Okay, in the, okay, the term that have j omega and the term that have no j omega. Okay, you can conclude that, okay, both sides will be equal. In this case, in the right hand side, it have no j omega. Therefore, the coefficient of the j omega in the right hand side will be equal to 0. Okay, 0 equal to k1 plus k2 j omega. Okay, and another one term is here, the term that don't have the j omega, 1 equal to bk1 plus a bk2. Okay, you have two equations, two unknown. You can determine k1 and k2 in the term of a and b by here. Okay, after you get here, you can see that you substitute k1 and k2 in this bracket. Okay, when you factorize them into this simple term, okay, the term that you have in here, okay, I think you can determine the inverse Fourier from the definition directly, or you can determine them by the table. Okay, this technique is called the partial fraction expansions directly, or you can determine K1 and K2 by use the residue technique. Okay, we can alternatively compute the partial fraction expansion as follow here. K1 is equal to the whole term, okay, the original term 1 by, okay, the zero term in there, 1 divided by A plus J omega, B plus J omega, and multiply with the denominator of K1. Denominator of K1 is the blue term, okay, is A plus J omega. And after that, you substitute the pole of K1. The pole of K1 is mean you set the denominator equal to 0, determine J omega. In this case, the J omega equal to, set the A plus J omega equal to 0, you get J omega equal to minus 1. Okay. Okay, next one. You determine K2 by the simple manner. Okay, the same manner. Okay, K2 equal to the original term. K2 equal to the original term. Okay, multiply with, okay, B plus J omega, substitute the root of them, okay, the pole of them, okay, the pole equal to, when you set B plus J omega equal to 0, okay, J omega equal to minus B, okay, substitute every J omega by minus B, okay, after you multiply them, okay, you get K1 and you get K2. You can see that the result will be the same as the previous, okay. After you get the partial fractions techniques, okay, after you apply the partial fraction technique and you get the result of the yt into a simple term, okay, you can evaluate the inverse Fourier transform. Sorry. Okay, inverse Fourier transform. Okay, by use the table or by integrate by yourself. 1 divided by A plus J omega, you integrate them. Okay, therefore in this term you get the Fourier transform of 1 divided by J plus J 1 divided by A plus J omega equal to e power minus at ut. Okay, and this term is, okay, is B plus J omega. We will provide you E minus BT ut. Okay, multiply with the coefficient of them. Okay, the key of that, okay, you can see that the key of this process is how to determine, how to apply the Fourier transform to the symbol signal and the symbol impulse response. You multiply them first, okay, and when you get the result in the Fourier transform, okay, you maybe use the partial fraction to make them into the simple term, okay. If you not, okay, yeah, some of you don't want to determine them directly, you don't use the partial fraction in this step. Therefore, you can, if you think you can integrate the whole term directly, you can, okay, but the answer is very difficult one, okay. Now, okay, okay, yeah, this question will be force you to apply the convolution property, okay. You can see that we have the sinc function, okay. You can use the table to determine the Fourier transform. I think the sinc function is very difficult one, right? Therefore, it's impossible to determine the convolution of two sinc function in time domain, because if you flip the sinc function, it's still difficult. You integrate them, it's almost impossible to find how many intersection pattern it has. Therefore, you have only one way to determine the solution in this case. You convert the sinc function into the Fourier transform and change them to be a simple multiplication instead, okay? Let's do it now, okay? And if you finish them, okay, I will provide your solution, okay? If you finish them, post them in the meeting chat and I will check it for you, okay? Any question? Capture this question, okay? Okay, and I will stop sharing the slide in 5 seconds. 4, 3, 2, 1. Okay. I give you, okay, 30 minutes, okay? Let's do it now quickly, okay? And I provide you complete solution soon, okay? Okay, before I check your attendance, okay, 20 student is here. Open the camera, okay, to see what about yourself, okay, to identify yourself. Before I loading your attendance list.ไงรัฐพลยิ้มเลยข้อนี้ง่ายเหรอ
ทำไม่เป็นเลยค่ะ
เอาหา Fourier transform ของ sinc function ก่อน sin t หาร t ถ้าหาไม่เจอโดยตรงก็ไปดูใน table มีหนังสือไม่ใช่เหรอใช่ไหมไปดูดิใน table มันแมปยังไงนัชชยาเป็นไงบ้าง เขียนนะรัน MATLAB image processing เสร็จยัง
ยังค่ะอาจารย์
แล้วชนนิการน่ะรันเสร็จยัง ไม่เสร็จโอ้ สุวรรณัฐวันนี้เข้าเรียนได้ด้วยเหรอ
ผมเข้าตลอดอาจารย์
จริงอ่ะไม่เคยจะเคยเห็นหน้าเลย
ไม่ผมเข้าผมใช้ iPad เข้าอาจารย์ ใช้อีก ID หนึ่งเข้าครับ
โอ้โหเอางั้นเลยเหรอ เนี่ยพวกขาประจำเนี่ยชินอารมณ์ที่เข้าบ่อยอยู่ใช่ไหมถ้าไม่วันไหนไม่มีแข่งรอบดึกก็คงไม่เห็นหน้า พัทรนันท์นี่เห็นบ่อยอยู่ ชนนิการนี่ก็นะ ชนนิชาใช่ไหมผมจำสีผมได้ แปลกๆ
ชนทิชาค่ะ
ชนนิชานี่ก็เห็นบ่อยอยู่นะปรินซ์นี่ก็เห็นอยู่เยอะอยู่เป็นไงรัชตะวันใช่ไหม
yes
yes รัชตะวัน quickly okay I give you another 15 minutes okay and provide your solution to know how to compute that okay the question in the final will be more difficult than this level okay therefore you must prepare yourself well for the real final is Hello? If you finish this question, you can do the next question, okay? The question is show you in the book, okay? The question that I order you to do is the question number, okay, 5.16, okay? You can do so 5.17 and 5.18, okay? And maybe in 5 minutes, I will provide you solution for this question, okay? You will do another, okay? It have 3 questions, it's about this section, okay? But, okay, you do, okay, the 16 and the 16 and the 17, okay? Follow that step.ใช่ครับผิวมันเนี่ยมันอาจจะหนาวแล้วผิวมันก็ไม่ค่อยได้นั่นมันก็เลยไปตากแดดจะได้ไม่คันนอนตากแดดมันเป็นหมาแม้ว่ามันเป็นหมาที่มีบุญนะมันอยู่กับเราใช่ไหม20มันจะไม่ยอมตายมันถึงได้มีอายุยืนนะอาหารการกินมันก็ไม่ต้องมีปัญหามันก็กินอาหารที่เละๆใช่ไหมง่ายๆ
ถ้าไม่ติดว่าได้ลาเวทส่วนจะช่วยนะ
แล้วปิยธิดานี่อยู่ที่คณะเหรอเนี่ย
ใช่ค่ะอาจารย์เข้ามาทำโปรเจกต์
โอ้ยังว่าอยู่ว่าแบ็กกราวด์คุ้น
ค่ะ
ๆอ๋อเหรอไม่กลัวติดโรคไม่กลัวโควิดเลยเหรอหรือว่ากลัวสอบตกมากกว่าก
ลัวตกมากกว่าค่ะเทอมสุดท้ายแล้วค่ะใกล้แล้วค่ะอาจารย์
อ๋อเหรอเอาตั้งใจนะไอ้หนู Okay. I will provide your solution for the first one. Okay, the first question first. Okay. Yep. Okay, for the first question is here. Yep. Okay. Okay. Okay, this question asks you to determine the convolution between two sinc functions. The sinc function is very difficult in time domain plotting and difficult in the direct convolution. Okay, but you know that okay from the convolution property, okay, you can convert the sinc function into the Fourier transform. From the Fourier transforms pair, okay, the sinc function have its Fourier transform shape to be the rectangle. Okay. The rectangles omega by 2, okay, is normalized by pi, okay. Two sinc function is the same, okay, two rectangle. Now, if you convert the two, okay, fortunately that's the first function is the sinc, the second is the sinc too, it's the same, okay. Now, the output equal to the convolution between two sinc function or the Fourier transform of the multiplication of this signal, okay. The Fourier transform of the sinc function equal to the rectangle, the simple multiplication between two rectangles. Okay, the first one is the yellow, the second one is the blue. To make you more understand, okay, give you here, okay, pi multiply is get you pi square, okay, and the rectangle multiply with the rectangle. In order to give you more understand, you must plot the rectangle graph first, okay. The rectangle is here, okay. The frequency is okay if the center is at the 0, okay. The y of them is 1, okay, in the omega point of view. The view x1 is here, x2 is the same. You can see that x2 is the same. When you multiply them, okay, the signal is have 3 pieces of them, okay. 0, the first one is the 0. 0 multiply 0 give you 0. Okay, you multiply them. Okay, and pi multiply pi give you pi square. Give you pi square. 0 multiply 0 give you 0 again. Therefore, when you multiply between the rectangle and the rectangle, give you the rectangle too, but the different shape. In this case, the y of the rectangle is the same. Therefore, the result will be the rectangle the same size. And you convert, okay? When you convert, okay, pi rectangle omega by 2 give you the sinc function. Convert them back in here, okay? Give you the result will be sinc function. Therefore, it's very weird a little bit one, okay? The convolution between the sinc function and the sinc function give you sinc function too, okay? Okay, the next one, the next question will be, okay, next question is here about the sinc square, okay? Yeah, sinc square and convolve with the sinc. Sinc square you already determined from the previous one, right? The sinc square is here, okay? The sinc and the sinc square is here, okay? And convolve with here, okay? Sinc square you can determine them, okay? I will give you another 15 minutes, okay? And provide your solution, okay? And we will start about the multiplications property. No. Hello, no one finished the second question yet?
I don't know how to do this, Ajahn.
Really?
Yes.
Okay. I will provide you some guideline. Okay. And only half. Okay. I will provide you solution only maybe partial of that. Okay. And the next lecture. Okay. You will continue until the finish one. Okay. Because I think if I don't provide you some, okay, you don't know how to do them. Okay. 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 Does this question ask you to determine the sink square convolved with the sink? The idea is the same, okay? The idea is the same. How is the same, okay? The sink function is a rectangle, right? The sink square, what about the sink square? It's here, okay? The sink square will be give you in, okay? It's about the, okay? Yes, okay? The sink square, okay? You can see that when you determine the sink function, okay? Two sink function in time, okay? You can take the convolution in the that's okay in the time domain. Okay, I will better than that. I think okay. I will provide you some okay, some technique first. Okay, now okay, from the multiplication property first. I forgot that. Okay, the multiplication property is okay. It's a reward process. Okay, but some of you may think that the multiplication will make you more difficult, but no. Sometimes it's easier. Okay, it means if you multiply the signal in time. Okay, you multiply the signal in time, it equal to the convolution in the frequency domain. Okay, the way to take the convolution is the same that you take in the time domain. You only change t to be omega instead. Okay, and in this case, when you take the convolution between them, you divide by 2 pi first. Okay, 2 pi. Okay, I will tell you how to determine okay the sink square function by use the multiplication property first. Okay, the multiplication property is very important in the moderate application. Okay, is this hello?
Your screen is not shared.
Oh, sorry. I don't share the slide. Sorry. Okay. Can you see that? Multiplication just here. Okay. The multiplication is mean you multiply the multiplication's property. Okay. If you have the signal xt, you have the Fourier transform of them x omega, ht, h omega. If you multiply them, you know that the way to multiply is very simple, right? You multiply them, yes, it gives you the convolution. Okay. You may be think why I must compute them in the frequency domain because the convolution is very difficult. No, sometimes it's more easier. I will show you. Okay. Okay, sometimes the left side is easier, sometimes the right side is very easier. Okay. If you multiply the signal in time, it equal to you take the convolution in the frequency domain. Okay. This technique can the application of the multiplication property, it have two main application for now. The first one, you can determine the complex function. The second one, we use them in the analysis of the modulations in telecommunication field. Okay, the multiplications property is very important in the modulation application because the Fourier transform map the multiplication of two signal into the convolution or the modulation of the Fourier transform. Okay, in general, when you would like to modulate any signal, we frequently multiply the signal with a sinusoidal waveform. It means you convolve with them or you modulate them. Now, the application of them is here. Okay. Yeah. The idea of them is here. Okay. If the signal in the frequency domain is here. Okay. Why we use them in the modulation? Very simple. Okay. This example will be provide you this idea. I think everyone know about the AM or the amplitude modulation. Okay. Even though I think no one or none of you will be listen the AM. Okay. Even though me. Okay. Almost all listen only the FM if you can. Okay. Now, if ST SJ omega is my voice, okay, the voice that I would like to transmit in the communication field. Let's ST is the signal that have the spectrum in this form. It means okay, my voice have the frequencies. The maximum frequency is 4 kHz at most. Okay, you modulate them. Okay, you would like to modulate them. How to modulate them? You multiply my voice with the chord function. the cost in general at the frequency that very high when you compare from my voice. Okay, for example, in the AM, okay, you moderate them in the channel maybe 100 megahertz, 90 megahertz, something like that, the megahertz, right? But my voice only kHz. Okay, therefore the frequencies that you moderate and the short frequency is about 1,000 times. Okay. Okay, the signal that I would like to moderate, okay, I multiply them by the impulse function, okay, the cost function. The cost, okay, the Fourier transform of the cost is here. Okay, maybe 1,000, okay, is here. The cost function, the Fourier transform of them give you the rectangle, right? The cost function, the Fourier transform is the impulse, okay, to impulse function. Now, when you moderate them, okay, when you moderate them, what about its meaning? Its meaning, okay, the signal in time is very difficult, right? You don't know what about my voice shape, okay? The shape of the signal is very difficult. Therefore, if you plot them roughly in the frequency domain, it's more easier, okay? You know that my voice will be in this band, okay? The convolution, okay? You know that the impulse function is the identity of the convolution. Anything convolved with the impulse give you that thing, but shifting by that position. Okay, therefore the green one convolved with this impulse will be give you the same function. Okay, but shifting in the left hand by minus omega naught, and convolved with the right impulse give you the same function, the same shape. Okay, but shifting in here. Now the signal is already shifting. It's already shifting in that frequency's point of view. My voice is already shift the frequency to be very high one. Okay, therefore my voice is very high frequency. No one in the world can listen them. Okay, it's already broadcast in the air. Okay, until you would like to receive them. Okay. Now, the idea of the moderation, okay, the relationship between them is the original signal in my voice. Okay, this is the signal, the carrier signal. Okay, the channel that you would like to listen in the radio frequencies 1,000 megahertz. Okay, 100 megahertz, sorry, 100 megahertz, 90 megahertz, okay, the same, okay, and this is the signal that you already moderate. Now, all will be show you in the frequencies point of view, okay. Now, how to show you in the time domain. The time domain is my voice is about here, okay, and okay, the carrier signal will be the cost function, right? The cost function that have a very high frequencies, okay. You multiply between the carrier and the information signal or the message signal, okay. The result is here. You can see that, okay. The signal, the envelope of them, the magnitudes of them will be in the green, okay. But the detail will be the data that you transmit will be in the sinusoidal waveform. But the magnitudes or the amplitude of them will be shared. Therefore, in this case, you can see that the amplitude of the carrier will be carry the masses. That's why we call this technique to be amplitude modulation. The amplitude will be shared. Therefore, we call them the amplitude modulation. Okay. This is the signal that I think everyone will be touch them every time. Okay. Because in the air, we have 1,000 or the million signal in this form, but you cannot listen them, you cannot see, and you cannot hear them. Okay. If you would like to listen this signal, you must demodulate them. How to demodulate them? Okay. The key, you must know omega naught. You must know the frequency that you would like to modulate. The same idea that when you would like to listen the radio, you know that, okay, hey, today I would like to listen the radio at the channel 90 megahertz or 103.5 megahertz or something like that, okay? Therefore, you must know about the frequency that you would like to listen, okay? And the way to modulate the AM is very simple. You only multiply the moderate signal, the green signal, by that frequency again. You only multiply them again. Okay. Now, okay, this is in the frequencies domain that we analyze. Okay. Let's RT will be the signal to have this spectrum or the carrier signals. Okay, that already moderate. Okay. Now we would like to demoderate them. The way to demonstrate them, okay, you know that you would like to multiply them by a chord function again, right? The Fourier transform of the chord function give you the same, the two rectangle, right? At that frequency. Now, when you convolve between them, what happened? You know that, okay, the first one, the original signal is here, right? Okay, the spectrum of the original signal that carrier, okay, that broadcast in the air is the red one, okay? The first left hand, okay, you convolve with this impulse. Anything convolve with this impulse give you the impulse, but shifting to that frequency, right? In this case, you have two impulse. Left hand shift in the left hand by omega naught and shift in the right hand by omega naught. Therefore, this signal, this spectrum will be split by 2. Okay, by you take the convolution by this. Okay, and the right spectrum will be the same. Multiply by this, you shift in the left hand and shift in the right hand. Okay, therefore, now the result will be here. What happened? You can see that the signal will be already shipped to the original, the same as the original, that is B, right? Therefore, in this, but it still have some this spectrum and this spectrum, right? We have the left hand and right hand spectrum that is uninteresting file. We would like to restore here. The way to restore is very simple. Okay, you set them to the low pass filter. Okay, you create a simple low pass filters. Okay, low pass filter. Okay, and you already get the original message back, right? Originals my voice back. That's why the technique that you demoderate them. The technique that you demoderate them is not create the low pass filter, but you create here the sinusoidal waveform to multiply by the incoming signal. Okay, and you get here and you moderate that. Okay, the next one, another one application of the Fourier transform that you frequently use is to solve the signal that very difficult in time domain. Okay, when you have this, okay, psi t divided by t, psi t divided by t give you two sinc function, right? Two sinc function. Okay, two sinc function. Okay, this first one is the sinc function, second one is the sinc function. Okay, you have two sinc function, okay, but it multiply in time. If you multiply them first, if you multiply them, give you sinc square. You don't know how to determine the Fourier transform, right? In the assignment that I give it to you. Okay, if I don't give it to you, you don't know, you don't realize is how difficult to solve them. Okay, and you by your skill in the calculus 1, calculus 2, calculus EMAT, you don't know how to solve them. Now, we will give the chance to solve them. Okay, even though you cannot integrate them directly, but you can take the advantage from the Fourier transform. Okay, now you see that. Okay, the Fourier transform of the sinc function give you rectangle, right? Give you rectangle. Okay, the Fourier transform of another sinc function give you another rectangle. In this case, okay, we intend, okay, the questions, okay, already decide that two sinc functions that have different in shape. Okay, okay, you have the rectangle and the rectangle, but both of them is not multiply, right? Both of them is convolve. The way to convolve the signal is not too difficult. When you see, hey, it's convolved in frequency domain, it's impossible to do. No, very easy. Rectangle 2t and the rectangle 3. Okay, when you see omega, the same that you see them in time t. Okay, you plot them first. Okay, when you plot them, omega, the rectangle is here. The first rectangle. The second one is here. The second rectangle. The convolve between two rectangles, where is easy one, right? I think everyone know how to take the rectangle. Okay, you fix one, you maybe fix, okay, x2. Okay, flips the x1. Okay, when you flip the x1 chip in the most left hand, try to find how many intersection pattern it have. And in this case, it have 5 intersection pattern. Okay, if x1 is moved in the very most left hand, okay, it have no intersection between two rectangles, right? And have start of the intersection and partial intersects, okay, and okay, leaving and no intersection. The result will be give you in this form. Okay, therefore you take the convolution in frequency domain when you get here. Okay, after you get here, it's already result of the Fourier transform, okay, of the rectangle. You model the rectangle, okay, and you can find the Fourier transform of them, okay. You get there, you can restore them first, okay. Remember that, okay, and you can take in the previous exercise, okay. The Fourier transform of the sin square will be give you here, is, okay. If it's a sin square, it's a perfectly matched, okay. It means the signal will be matching perfectly, okay. X1 and X2, it reduce the intersection into 4, okay. It have no here, okay. It have no intersection, partial intersection, and okay, and leaving immediately because the side, the y of the rectangle is equal, okay, and leaving. Therefore, the result will be give you about the triangle, okay, shape instead. Okay. Sin square, yeah. The question of the sin square we show you in here. We'll ask you, okay, yeah, the same idea, right? Okay, takes the Fourier transform of them, okay, by this idea first. Okay, let's do it, okay, and don't worry about that, okay. In fact, I can provide your solution immediately, but I think if I give you immediately, okay, you don't have the time to think what happened and how to do them, okay. And if the question is modified and more difficult than this, you don't, okay, you don't have the incentive to do that, okay. Now I provide you partials of the solution first, okay. The sin square, okay, that we take in the previous exercise. The sin square, separate them into sin function, okay. Each of them is the rectangle in the same side, and if it in the same side, plot them in the figure 6 domain, take the convolution. Okay, capture this, okay, and do that 2 questions, okay. Any question? Okay, try to do that, okay. Next time, okay, I will provide your solution, okay. Okay, and the one last thing, okay, for the last part of these lectures, okay, the Fourier I think is have only 2 times for the lecture them, okay. This is, okay, this time and the next time, okay. This is a summary of the Fourier transform table pair, okay. The table figure you can find in the books, okay, in the book, okay. You can use the post-it to mark it or something like that. That easy to open them, okay. Some common term that the Fourier transform will be used, okay. The following table have assembled a list of the many basic important Fourier transform pair. Using this Fourier transform pair, we can easily determine the Fourier transform and the inverse of them, okay. This table, even though it's summary only a simple function, but you can modify them, create a more difficult function by combine the table with the property that you know, okay. The Fourier transform of the impulse give you 1, or the inverse Fourier transform of 1 give you the impulse. If the impulse is shifting, okay, you can see that this term, in fact, you can apply the shifting property. It equal to multiply by E minus j omega t, okay, j omega capital T, multiply with 1, okay, multiply with 1 give you that thing. Or the reverse, okay. The Fourier transform of 1 give you impulse, but you normalize them by 2 pi, okay. If you multiply by, if you shifting them in here, if you shifting in the frequency, multiply by e power j omega naught t, okay, in time, okay. Next one, the Fourier transform of the cost function that show you in the previous example, okay, give you the 2 impulse function shifting by that frequency, 1 in the left hand and 1 in the right hand, okay, shifting by omega naught frequency. And don't forget to normalize, multiply them by pi, okay. For the psi is close similarly to the cos, except 2 things. One, okay, one is here, the one, okay, the frequency is okay, the magnitude of them, 1 is positive, 1 is negative, okay. And here, okay, unit step, okay, unit step and the inverse of them, okay, is a time reversal, okay, shifting them, okay. The decaying exponential e minus at ut, okay, the Fourier transform of them give you 1 divided by j omega a, okay. If you multiply by t, okay, give you square, okay. And the rectangle, the Fourier transform of the rectangle give you the sinc function in the frequency domain, or the Fourier transform of the sinc function or psi t divided by t give you the rectangle. You can see that, in fact, two formula can determine by the duality, but already provide for easily and fasting using, okay. For the size function we have here, okay, 1 for time greater than 0, 0 at this time, and minus 1 at that, okay, give you 1 divided by j omega, okay. Impulse train, okay, the Fourier transform of them give you the same impulse train, okay, but shifting at that frequencies. Normalize them by 2 pi divided by t, okay. All table, okay, is already show you in the books, okay. You only apply them to know how to apply them. Okay. The last topic that we discuss in the next time is about the analysis and the classification of the LTI system using the Fourier transform. Okay. This section will give you the more broadening and the more closings how the Fourier transform apply on the real world. Yeah, you can see that if you have the system, you have the input, you have the output. Instead, you compute them by here. You will compute them in the frequency domain or the Fourier transform. This idea is not only used for the Fourier transform. It's used for the Laplace transform, set transform. And the Laplace transform is very important in the system analysis, okay? If some of you already study in the mechatronics, okay, you have a chance. Or maybe in the electrical engineering, you have a chance to study in the feedback control. This idea is already used in the feedback control too, okay, in the near futures, okay? But we will analyze them in the detail later, okay? Any question?
No, อาจารย์
Okay. If we have no question, okay, see you next time. Good luck.
See you ครับอาจารย์ thank you ครับ
ครับผม
Thank you, John.
Thank you,
You're
Ajahn.
welcome.
Thank you อาจารย์
You're welcome.
ขอบคุณครับ
สวัสดีครับ